The title of the talk is Waves in Space-Time and Propagation. This is module 1 and lecture number 1. So, I start with the description of the underlying space-time where a wave usually propagates, and it is called the propagating wave. Generally, the description of space-time that enters in any description is important. For a system which is unbiased and is not influenced by any external agent, the space-time is supposed to be homogeneous and isotropic. So, if we are watching any disturbance that is coming across space-time in a homogeneous and isotropic space, the signals or the nature of the signals will be indistinguishable from each other when it is viewed from any angle and in any direction. This is a general property. But however, if there is a direction that is for some reason comes into play into a description of the space-time, then this isotropy and homogeneity of space-time gets altered. To give you an example, let us talk of a situation when we have a source that is stationary in some frame of reference. So, let us start with the leftmost figure in the picture that is being shown, and there are 3 panels towards right, and each panel represents someone moving towards this observer or this source at different speeds. The object that is important is the introduction of this observer and his movement in a particular direction introduces a preferred direction to the system. And so, for instance, for a person who is walking towards the source, when he looks into the source, for him the light source, its frequency and distribution almost remains unaltered. However, let us replace this observer who is walking towards the source by a speeding motorized vehicle. Now, you see that the v at this stage is much larger than the velocity of the gentleman who was walking. So, as a result, the distribution of intensity of the source has become different, and not just that, the spread in the length in the direction of propagation has become shortened, whereas in the plane that is perpendicular to the direction of motion, there is nothing very noticeable. And if we still replace this moving object by a vehicle which moves much faster than the motorized vehicle on the earth, then we will see that it just frequency that gets changed, and not just that, the amount of light being squeezed down in the z direction is far more than what we had experienced in the previous two situations. So, to elaborate on this particular aspect a little more, let us say that we actually talk of two frames. One is a primed frame and one is an unprimed frame. The primed frame, which we represent by quantities, those are not primed, presents a frame of reference that is at rest relative to the one, another primed one, which is moving with a velocity v, and for simplicity what I have assumed is it moves along a direction which is same for both the systems. Now, if we have a frequency of light that is given by omega, then in the primed frame, what the observer will see when it is moving, it will see that this particular frequency, which is omega years before, now has become different, and let us call this by another quantity which is omega prime. Now, these two frequencies omega and omega prime can be, number one, omega is greater than omega prime, omega is less than omega prime, and omega remaining the same as that of omega prime. So, the question now that arises is, under what condition these frequencies undergo these three different kind of changes. So, number one, when omega is less than omega prime, this can happen when the observer is actually moving towards the source with some velocity. The situation when omega remains the same as omega prime is a situation where the observer does not move with respect to the source, and the third situation is when the observer actually recedes from the source. You might have heard already in the when you are going through courses in astronomy or the physics of stars or galaxies, that people often talk of signals getting either red shifted or blue shifted. So, this shifting, whether you call it red or blue, is a phenomena that is due to the motion of the source, whether it is moving away from the earth or it is moving towards the earth. These are the two situations when we have red shifting or blue shifting. Now, to give you a little more imaginative picture, you know, our atmosphere actually acts as a filter. It does not allow lights of all frequencies to come down and fall on us. So, depending on the motion of the source or that of earth, there are some frequencies of light that could always be shifted to be in the visible region and be detectable as a consequence. Now, another important point that enters into the discussion is the angle, that is, whenever you observe an object, in most of the situations, these objects are making some angle with respect to the source, or the source makes an angle with respect to the observer. So, is it that only the frequency gets changed due to the relative motion of source and observer, or the angle of observation also undergoes modification? As it turns out that if the motion is not strictly linear, making an angle, let us say phi, then this angle phi also undergoes a modification because of the relative motion between the source and the observer. And this angle can increase or decrease depending on whether the motion is along towards the observer or it is away from the observer. The next picture that we have on the frame is the distribution of the energy of a plane wave that is coming from a source and moving towards an observer. On the top left panel, you can see that there are two purple colored patches, and what it represents is that if there is no motion that is taking place between the observer and source, the energy of the light that is coming, that remains same, and what also remains same is their angular distribution. But now, let us say that these two frames are not at rest with respect to each other. One is moving with respect to the other with some velocity v. Then you see that in the second panel, top right, the red striped patch has turned into a purple striped patch, and the height actually represents the intensity. Now, if we look at the side patches, those are yellow and green. They also do undergo a modulation, and the amount of modulation can be seen on the right top patch, that's, and next to the peak you can see the small humps that describe the patch. The relative difference between these patches in terms of their angular separation, when it is moving, when you observe it from a moving frame of reference, also undergoes a modification. In physics, more often we take recourse to a figure that is usually called the light cone diagram. In the light cone description, we take time to be on the left horizontal direction. So, once we accept this frame or accept this picture, then the whole space now gets divided into 3 regions. Region number 1, where velocity of light times time is equal to the spatial distance, and it represents a straight line, diagonal straight line moving towards the top right corner, and the opposite is in the top left corner. In this patch, things are connected and causal. However, on the other 2 patches, they are different. So, when there is a motion with respect to the other, this space time picture that what we have drawn here now gets slightly modified to the form that is shown on the right bottom corner over there. So, where we started the discussion, that was basically dealing with the homogeneity and isotropy of the space time, can be seen to be disturbed by the introduction of a vector which defines the velocity vector of relative motion between the 2 frames. And this vector also, depending on its orientation, introduces a angular dependence to the observables that we see. According to the special theory of relativity, there is something that is called transformation matrix that transforms the observables from one particular frame of reference to another. And this particular transformation also is known as Lorentz transformations. So, the idea is that this effect that we have just described should in principle be captured in terms of what we called is this space-time transformation from one frame to the other frame. So, the waves and its manifestations as a signal to the detectors when they are being considered should actually be respectful to this particular condition, what we have called motion, and that is captured by this transformation. So, many of these spectropolarimetric signals, they are assumed usually to be inert to the relative motion and relative orientation need not be so. So, this is the first issue that we would like to highlight, and the second issue is, light normally is a disturbance that is generated through electromagnetic interaction. So, what are the objects in the world that we know of that produces light? It must be producing light because light interacts with them, and there is a coupling between the two. And these materials, those interact with light, their state of matter or their state of or physical state also should be able to, or by just able to, it also affects the light that is coming from these sources. Let us take an example. Take an example which is pretty simple. I look at boiling water, I look at the flame of my oven, and I look at the sun, and we will see that these three things actually are in three different states, where their motion in their confined state is actually differ from each other. So, in principle, the light that propagates through them, these materials, also is going to affect the signal that you are getting. So, this is the second thing that affects your signal or our signal when we observe them in our observatory. This is the second state of, or second thing that we would try to highlight in this particular discourse. Okay. Thank you.